Hello my dear, welcome to the IMS GATE Academy. I hope you are all good and your preparation of the GATE 2023 is going to in a right direction. So myself Pragyabrat Tripathi, I am the faculty of IMS GATE Academy. So beta previously, hi Srinivas sir, hi, hello. So yesterday we will discuss few problems related to the heat transfer subject. Now today we will continue that session, and in that session we take again some beautiful and very conceptual question. So see beta, this question will definitely help you to score your GATE. See what happened, this is not only a question, this gives the insight of your concept also, where you have to find the theory, where you have to find difficulty to understand the theory, concept, theory, anything related to the concept. Now till 3 hour time of a span, you just go through that problem and see what is the level of the problem. Okay beta, definitely you may get something beneficial to you. Okay beta. So today's first question is that beta, see, this question is related to the convection, number first, and internal fluid flow and internal fluid flow. Beta, this type of question already asked in the previous year, but it is not that question. It is a different type of question which may be asked in the upcoming GATE examination or anywhere in the competitive examination. So this question is very useful. See and read carefully. Say the inlet temperature of the water, that means there is a water, right? So this question is convection and internal force convection. Internal forced convection. Internal forced convection. Okay beta. So the inlet temperature of the water is 30 degree. The length at the tube, that means length of the tube is 1 meter and dia of the tube is 15 centimeter. This is the dia, right? Dia of the tube 15 centimeter, right? The wall of the wall of the tube, this is tube maintained at a uniform temperature. This line is very important, I'm telling you. This is very important. Uniform at 70 degrees centigrade. That means there are two cases in the internal force convection. First is that constant heat flux or uniform heat flux or constant wall temperature. There are two criteria in which we can find the things which is parameter which is related to the heat transfer. So this question is the case first, that means a wall have a fixed temperature. See what is the practical significance of this question. See, if there is a tube, on that tube, the tube have a isothermal, that means the tube have a same temperature throughout. The tube have a same temperature throughout. How to make, think that beta, how to make the tube wall have a, how to make the tube wall at a uniform temperature, that means over the surface the temperature is uniform. How to think? You think that, sir, there must be condensation, there must be a phase change, over the surface. There must be a phase change over the surface. During the phase change of the fluid, the temperature will, temperature will remain constant. So this is the example. So you cannot judge that, sir, it is the case. No, it is a practical case in which one fluid have changed its phase. So during the change phase, latent heat will transfer, and that latent heat will use to change the temperature from inlet to exit. So this is the case. Got it? Now the bulk mean temperature at the exit. Now there is a one term very important. What is that beta? Bulk mean temperature. Bulk mean temperature. What is the bulk mean temperature? See beta, why we call the bulk mean temperature at the exit? See, simply they ask that, simply it may be asked like that, mean temperature at the exit. Temperature at the exit. Bulk mean temperature is that beta, see, there is a constant wall temperature and the fluid that is at inlet to exit, its temperature change. So at each and every cross section, the temperature difference will change. Each and every cross section of the tube, of the pipe, if you select any cross section, the change in temperature is changing. So we cannot find exactly temperature, so we can use bulk mean temperature. Bulk mean temperature, what do you think about the bulk mean temperature? The bulk mean temperature, it is a average temperature throughout any cross section. That means if there is a pipe through which the fluid is flowing, so from the surface to the center of the fluid, to the center of the pipe, temperature will vary. So how to make the uniform temperature as a cross section? You can just stir, you think like that, you just stir the fluid at a given cross section. That means if this is your pipe and if this is your temperature profile, beta, my dear, this is your temperature profile, think like that, this is your temperature profile like that. This is your temperature profile. It is not arrow. It is not arrow beta. In the temperature, this we cannot put arrow. So at any cross section, let's suppose this is our temperature profile. This is our temperature profile. So how to make this temperature as a uniform or as a bulk? You can think that we put a stirrer device, stirring the fluid, so that at that cross section, it is not like that we are anything physically put into the pipe and stir. No, you may think like that, how to make the fluid as a uniform at a particular cross section. So just stir that fluid so that the temperature at that cross section is uniform. That temperature is also called bulk mean temperature. That means average temperature. Okay, no problem at all. Now, so bulk mean temperature at the exit. We have to find bulk mean temperature at the exit. Okay, no problem at all. But there is some data is missing here. What is the data? I have a data. What is that? The density of the fluid. That means density of the fluid. It is given. Density of the fluid. It is given how much beta? 992.2 kg per meter cube. Okay. Thermal conductivity K, it is 0.634 watt per meter Kelvin. No problem at all. Kinematic viscosity, it is given 0.659 cross 10 to the power minus 6 meter square second. Okay. Now Prandtl number, it is given 4.31. Okay, no problem at all. And mass flow rate of the fluid in the tube, it is given 50 kg per hour. 50 kg per hour. Thank you, Bipin. Thank you, Bipin. This is given data. Okay, now we have to find the mean temperature या exit temperature of the fluid, the bulk mean temperature at the exit. What is the temperature at the exit? So first we draw, this is very important question I am telling you, for the internal force convection. So what is that beta? We add some page. No. Now see this is your tube, right? This is your tube and the fluid is flowing inside the tube. So fluid is flowing inside the tube. Fluid is in, fluid is exit. Okay beta, the temperature at inlet, it is given how much? 30 degrees centigrade it is given. Temperature at exit, I have no any idea. The wall maintained at a fixed temperature, Ts is equal to 70 degrees centigrade, which is constant. This is the model of the problem. This is the model, how to model that problem so that we can solve easily. Right, okay, no problem. Now, the length of the tube is also given. How much? It is 1 meter. It is 1 meter, no problem at all. It is 1 meter, no problem at all. Okay, beta. Right. Diameter, it is also given. How much? 15 centimeter. Okay. Now, this is the question. Now, we make a temperature profile. How to make a temperature profile? This is our temperature axis and this is our length of the tube. We take x direction. This is your x direction, have a length, and this is your temperature T. Right. X at this point, x is equal to 0, and at this point x is equal to L. X is equal to L. No problem at all. Okay, now we have to make the temperature of the fluid is constant. Temperature of the fluid is constant. And beta, see, this is 30 degrees centigrade, which is lower than the 70 degrees centigrade. There must be a fluid is heating. The fluid is heating. That means the temperature must be increased from that 30 degrees centigrade, but it is never cross the 70 degrees centigrade. The fluid maximum temperature at a infinite length, the temperature at the exit is 70 degree only. It is not much more at 70 degrees centigrade. So we can assume that there is a certain length, there must be the exit temperature is below that 70 degrees centigrade. In the ideal case, it will be at 70 degrees centigrade, but in ideally, for that case, we have to make the pipe as infinitely long. Okay, right. This is your 70 degrees centigrade. It is higher. We put this is your 70 degrees centigrade temperature. We put 70 degrees centigrade temperature. This is your 70 degrees centigrade temperature. 70 degrees centigrade, and this is constant throughout. Now, this is your 30 degree inlet. This is x at x is equal to fluid at inlet, at x is equal to L, fluid at exit. Now, this is your 30 degrees centigrade. This is your 30 degrees centigrade. This is your 70 degrees centigrade. Now, the fluid have its temperature increasing. The temperature of the fluid is increasing. The temperature of the fluid is increasing at exponentially. How? It is at exponentially. Right, in the theory, we discussed all the things, how the temperature varies exponentially. So the temperature varies exponentially, and it reach at exit temperature TE. This is your direction, fluid flow direction. This is your fluid flow direction. No problem at all. Now, we cannot put the direction of this. Why? Because this is a wall temperature. This is not a direction. So, intuitionally, we put the direction in this phase. Why? Because it is moving like that. Okay, no problem at all. Right, this is your wall temperature. This is your fixed. Now, that means this is constant. Now, this is your mean temperature. Tm, bulk mean temperature at inlet, bulk mean temperature at exit, it will vary exponentially. Okay, right. Now, there must be a heat transfer from the surface to the fluid. That means, see the beauty, beta. See the beauty when the fluid is approaching at exit cross section. when the fluid is approaching at exit cross section, the temperature difference is minimum. That means the heat transfer also minimum. Minimum the temperature change, minimum the heat transfer. Maximum the temperature change, maximum the heat transfer. So in the case at a constant wall temperature, first half of the tube have a greater heat transfer as compared to last half of the tube. You may think like that. That means, sir, during the first half of the tube, heat transfer is more as compared to the second half of the tube. Why? Because continuously the range of the temperature is reducing. So that beta, at each and at every cross section, if you select, the temperature change will vary. So if the temperature change will vary, so there must be an integration it is involved. Why? Because we cannot take direct difference between these two. We can integrate at a particular cross section. We find heat transfer at a particular cross section and temperature at a particular cross section, and that temperature will integrate from entry to exit, so that we find the total mean, right? Now, so this is your heat transfer. Let's suppose we take a cross section. Let's suppose we take a cross section beta here. We take a cross section of the tube. We take a cross section of the tube. This is your cross section of the tube through which heat will transfer. Through which heat will transfer. This is your Q. This is your Q. Heat will transfer. Through which heat will transfer. That means we take this cross section and over that the heat will transfer. This is the cross section. See, this is your cross section, and mind it, the heat will transfer through the periphery. Through the periphery. What is the area through which heat will transfer? See, if we select the area of the tube, this is your selection of this elemental part, elemental cross section. So what is the area through which heat will transfer? That means there is a periphery into we take, this is your dx. This is your dx and this is your perimeter P. This is your perimeter P. That means perimeter, that means a perimeter. That means there is a perimeter into dx is the area which is responsible to transfer the heat. There is a big confusion in the student to the student community. So what is the area of responsible area? So this is your not a cross section area, my dear. It is not a pi by 4 d square. It is your perimeter into distance dx. Perimeter into distance dx. So area which is responsible to transfer a heat is perimeter into dx. Always keep into mind. Always keep into mind. That means perimeter into dx. This is the area which is responsible to transfer of a heat during the constant wall temperature. Right. Okay, no problem at all. Okay, beta. So what is the heat transfer? So see, beta, this heat will transfer from wall to the fluid, and that fluid will rise its temperature from 30 to T exit. So what energy will take? What energy will take by the fluid from temperature 30 to TE? This is your mCp delta T, mass of the fluid, Cp of the fluid, and temperature difference, that means TE minus 30 degrees centigrade. Right? Okay, no problem. So heat transfer, rate of heat transfer, that means heat gained by the fluid. This is heat rejecting by the wall, at the wall, and heat gained by the fluid. That means heat gained by the fluid, mass flow rate of the fluid, Cp of the fluid into T exit minus T inlet. T exit minus T inlet, put all the value, and this is beta T exit T exit minus T inlet. T exit minus, let's suppose we take this cross section. Well, let's take support this one. So this is your what, beta? This is your M. So we take, this is your DM. This is your DTM. DTM. This is your DTM, a small DTM. So this a small DTM is your small t. This is your TE at this point. This is your TE at this point minus TE. So we can write in this element, during this element, why we select a cross section, we can write M dot CP into DTM. This is the same at this one. This is equation number first. What is the equation number second? Heat transfer from the wall to the fluid is a convection mode, from the wall to the fluid is a convection mode. What is the convection heat transfer from the wall to the fluid? This is the heat transfer. So this heat transfer by the convection and this heat transfer by the gain of its energy, internal energy. This is your, if we heat will taken by the fluid from the wall to the fluid, that energy is at internal energy. That means internal energy will increase. That means heat supply by the wall, to the fluid will converted to increase its internal energy of the fluid. So increase its internal energy of the fluid is what? So what is the, this is your internal energy increase, and what is the heat will given by the wall to the fluid is mode of convection. It is your H. Right, H, very important, H into wall temperature minus mean temperature at any point into the area. Which area? This is the peripheral area. What is that? This is your DAS. This is your DAS. Okay, this is your DAS. So this is the equation number second. Now solve this one, equate this. This is the energy balance. What is the internal energy will increase? The same energy will supply to the fluid. So this, from the energy balance, this is equal, that means M dot Cp dTm is equal to H T wall minus Tm into what is beta? P into dx. Now P into dx. Now this, see, so this dTm, very important. What is this dTm, beta? This dTm we can write like that, beta. We can write minus d T wall minus Tm. We can write. Why? Because if we differentiate is minus, this is a constant, T wall is a constant, so this is 0, minus dm will same. So we can substitute this one in this form. So if we write this equation further, d by T wall minus Tm divided by T wall minus Tm, will take this one, is equal to minus Hp divided by M dot Cp into dx. So this is your guiding equation. Always remember. Right? Now the problem is very simple. You can integrate this one. So from, if we integration, how it will integrate from lower limit is Ti, upper limit is Te. Length x is equal to 0 to x is equal to L. If we integrate it, this will convert into ln T wall minus T exit divided by T wall minus T inlet is equal to minus H is the average. This is a good manner to write. Why? Because beta, this is the average. We take H na. This is the average value. That means this is also constant value. So this is your H average into AS divided by m dot Cp. M dot Cp. Now, from here we can take Te is what beta? Ts minus Ti into exponentially minus HAS divided by m dot Cp. You don't remember this formula, always try to solve. Now, see, now the problem is that beta, now the problem is that here, what is the problem is that, see, we don't have H value, this is very important. We don't have directly in the question, there is no any information of H value. So how can you calculate H number first? Now you have all the values, Ts you have, Ti you have, mass flow rate you have, Cp you have, As you have, but you don't have a H value. So this is your now speed breaker. This is your now speed breaker. Just think how to calculate H value. See beta, if we calculate the H value from, we always go through the Nusselt number first. If we apply the Nusselt number, there are two criteria. What is that? One is your laminar flow or either turbulent flow. That means we have to check first the flow inside the tube is whether laminar or not. Laminar or not. So for number first, second, number third, for the criteria, what is the, for the criteria to identify the flow situations is only by the Reynolds number. So first you have to calculate the Reynolds number. Number third, but number again, if you calculate the Reynolds number, you have to require average velocity, and in that question there is no average velocity. See the beauty. That means this question, why the question, this question is very important. See the beauty. Why this question is very important. See, we don't have H value. We don't have H value. For the calculation of H, we have to find the Nusselt number. We have to find the Nusselt number. Now, how to find Nusselt number? Why? Because it may, then we find it is laminar or turbulent route, right? That means Nusselt number for the laminar and Nusselt number for the turbulent, these are two different things, right? Now, if we find the flow is laminar or a turbulent, if we find the flow of laminar or turbulent, we are finding the Reynolds number. Very important. Now, if you finding the Reynolds number, you must be find the average velocity of the flow inside the pipe. So that this question is very important. This question is very important. So we can take this question. Okay, now how to find the velocity of flow during the pipe flow? How to find the velocity of the flow inside the pipe? You have a mass flow rate. You have a mass flow rate. You have a mass flow rate. What is the mass flow rate? What is the mass flow rate? Density, area into average velocity. Density, area into average velocity. You have a density, you have an area. In that area there is a cross section area. You have area, you have a mass flow rate, then you can easily find the average velocity. Once you find the average velocity, find the Reynolds number. Once you find the Reynolds number, check whether it is a 2000 is less than 2000 or 22,000 or 2300, whether it is less than or greater than. If it is less than, though this is laminar. If we find that laminar, if you identify the flow situation inside the pipe, example, if there is a laminar, then apply the Nusselt number for the laminar. Apply the Nusselt number. From the Nusselt number, you can find the convection heat transfer coefficient. Once you find the convection heat transfer coefficient, you can easily find the exit temperature of the fluid. Yes or not? Exit temperature of the fluid. So start with that. First find mass flow rate is what? Rho into cross section area into V average. Yes or not? Yes or not? Yes, sir. Now you have a mass flow rate. What is that? 50 kg per hour. That means 50 by 3600 divided by what is the density? It is given, beta. Density is 992.2. Right? What is the cross section area? Pi by 4 d. D it is given how much? It is your 15 centimeter. That means 1.5 ka square. Right? Into average velocity. So we have average velocity is what? What is your average velocity? It is your 8 cross 10 to the power minus 2 meter per second. See my dear, this is your velocity, and see the beauty. This velocity is very less. This velocity is very less. So without calculation of the Reynolds number, you can say that yes, this is laminar. Yes, this is laminar. Why? Because if there is a pipe of a 15 centimeter and velocity this much, that means 0.008 meter per second, this is your velocity. See the beauty. Such a range of a velocity will always gives that a flow is laminar. But we will check, no problem. If you have, then we will check. What is the Reynolds number, beta? What is the Reynolds number? RE rho V average into characteristic length, and the characteristic length for the internal flow through the pipe is diameter divided by dynamic viscosity. Right, but we have from that question we have a kinematic viscosity. So we know that beta kinematic viscosity is dynamic viscosity. Yes. What is the kinematic viscosity? Is dynamic viscosity by density. Right? Dynamic viscosity by density. Right? So, okay. So, beta, from here we can write like that: V average into D of the pipe by kinematic viscosity by, that means V average diameter of the pipe divided by kinematic viscosity. Put this value. V average 8 cross 10 to the power minus 2. Diameter of the pipe is what? 0.15. Kinematic viscosity is what, beta? 0.659 cross 10 to the power minus 6. So the velocity is Reynolds number is 183. See the beauty. This is a very, very low Reynolds number. That means this is less than 2300. That means flow must be laminar. Flow must be laminar. Now, if you have the flow, if you have the information about the flow characteristic, whether it is laminar or turbulent, then we are comfortably apply for which case the Nusselt number is. For which case the Nusselt number is. Okay, beta? Now, so for the laminar and constant temperature, that means, see, what is your model? See, this is your, see, beta, very important. You may write always, this is your habit. This is question of convection and the velocity it is given. Velocity it is given through the, so there is a forced convection. This is your inside the tube, so internal force convection, and this is internal force convection, and this is your Reynolds number less than 23,000. That this means laminar, and this is also surface temperature is constant. So this is your model. This is your model of the problem. This is your model of the problem. Always keep in mind, this is your model of the problem. Right. So beta, for the laminar and constant wall temperature, Nusselt number Nu is equal to H D by K. K is the fluid, is equal to 3.66. If you don't know, then you cannot solve this problem. Please, this is your constant wall temperature. This is the condition of a constant wall temperature. Right. You have a diameter, you have a thermal conductivity. You can easily find what is the convective heat transfer coefficient. So the convective heat transfer coefficient from here you can find 15.5 watt per meter square Kelvin. Once you find the convective heat transfer coefficient, put that in this equation, put the value back in this equation. So put all this value, if you put all this value, see the beauty, put all this value, that means exit temperature is equal to 70 minus 30 exponentially into minus 15.5 into pi by 4 d.15 square divided by 50 by 30, 600 mass flow rate into 4174. This is your CP. Solve this one. This you have to find 30.18 degrees centigrade. See the beauty. That means 13.7 degrees centigrade. That means, what is that? 13.18. It is a very minimum temperature change. That means there is a very short length. Length is very short. So the option is C. The option is beta C. Okay. Now, this is your problem, which is very, very important. How to solve? This is your equation. Thank you, Pratik sir. Now, it is okay, beta. Oh, this is your next problem, which is related to the Hissler chart. See the beauty. This is the problem which is related to the Hissler chart, and many of you will not prepare this chart. Why? Because sometime very easy question asked in the GATE. Why? Because they know that you cannot study deeply of the Hissler chart. See, my dear, that's why we are select this question, so that you can boost your concept. Right. Hissler chart are used to determine the transient heat flow. What is the transient heat flow? What is your transient heat flow? Thank you, Pratik. What is the transient heat flow? Transient, that means the property. Transient, that means beta, the property of the body, that means the temperature within the body not vary with respect to space, only vary with respect to transient. That means unsteady. That means the property of the body which you select to the study, for the study, that body is changing its temperature unsteady manner. That means with respect to time. See beta, temperature is a field, like a velocity is a field. So temperature is a function of position and time. That means the temperature is non-uniform and unsteady. If the temperature is not a function of position and it is only the function of time, that is called transient temperature distribution within the body. That is called transient temperature distribution of the body. हाँ, Atul, today's we'll cover all the questions related to mixing. No, not a special topic for that. We are taking a random question randomly so that you can get a practice. We are touch all the all the topic of the heat transfer, all the topic like yesterday. But the today's problem is differ from that one. Why? Because the level is something improved. The level is something higher than the previous lecture, than the previous session. Okay, so you don't bother about that, sir, which topic is covered. See, I am not covering any topic. I am not covering any topic. I am covering heat transfer. I am covering only heat transfer. So enjoy heat transfer. That's it. Don't think extra. Okay. See the board. Temperature, it is a function of temperature. It is a function of time. Okay. So this is called unsteady. Pratik sir, your option is B. Your option is B. Okay. Let's check. Let's check. Let's check. So the Hissler chart are used to determine the transient rate, flow rate and temperature distribution. That means beta, from the Hissler chart we can see, this is the one concept also. Hissler chart, someone asks you, what is the use of Hissler chart? What is the use of Hissler chart? So you can say that, sir, Hissler chart is used to transient heat flow and temperature distribution within the body. Yes or not? So question itself gives one concept, so that I am taking this question. Question itself gives the concept. So see the level of the option. Option also gives you concept. So Hissler chart, remember always, Hissler chart is used to determine heat transfer and temperature distribution, but that heat transfer is transient. That means temperature is only the function of time. It is not a position. Yes. Okay. Now the option is solid possesses infinitely large thermal conductivity. Solid possesses infinitely large thermal conductivity. Internal conduction resistance is smaller than the convective resistance is large. Internal conduction resistance is small and convective resistance is large. We'll check. Internal conduction resistance is large and convective resistance is small. Both conduction and convection resistance are almost equally significant. प्रतीक जी, आपने मिस्टेक कर दी. See, this option, internal conduction resistance is small. Conduction resistance is small and convective resistance is large. It is not a good option, or it is not a right option. This is your right option. That means, see the beauty. We are applying the transient heat conduction, one of the non-dimensional parameter known as Biot number. And Biot number is a decide. You can assume that your system which you studies, whether it is lumped or not. See, so in the lumped analysis, beta, what is that? I give you one sort of this one. So in the lumped analysis, beta, that means a Fourier, when you study the lumped analysis, that means conduction resistance is minimum, internal conduction resistance is small and convective resistance is large when there is a Biot number. If you study the Biot number, then this is okay. That means from here it is right that Biot number is significantly used in which situation. This is your right option. But when the Biot number have a limitation, that means its limit. How to do? That means whenever the conduction resistance within the body and convection resistance both are equal, then Biot number is not applicable. So in that case, Hissler chart is used. That means when the conduction resistance is equally important as compared to the conduction resistance with respect to the convection resistance, then the Fourier chart come into picture. and that Hitler chart come into picture, and that Hitler chart is used to find the transient heat transfer and temperature distribution. Yes or not? Okay, so option D is correct, but we are giving the inside of this. What is that? See the beauty. See, Hitler chart. Sorry. What is that? What is that? Hitler chart is significantly used when you have know the Fourier number. What is the Fourier number? FO, this is known as Fourier number, and this is what beta? Directly we can write alpha T by length ka square. See, what is alpha beta? We know that alpha is thermal diffusivity. And mind it beta, what is the difference between heat transfer and the fluid mechanics? There is a one difference. Diffusion of a heat. See the beauty. Diffusion of a heat, we can measure the parameter alpha, and momentum diffusion, we can measure the kinematic viscosity. From the kinematic viscosity, that means alpha, thermal diffusivity, and kinematic viscosity both have a same nature, both gives the diffusion. One is a heat diffusion, other is a momentum diffusion. So the alpha have a same unit of kinematic viscosity. Why? Because it is the diffusion of the heat from the surface to the fluid. Yeah, to the fluid from the surface. That means this is your heat diffusion. So that from the heat diffusion, you can draw the thermal boundary layer. And the diffusion, this ratio of the diffusion, that means which diffusion is strong. Either thermal diffusion is strong as compared to momentum diffusion, or momentum diffusion is strong as compared to thermal diffusion, or both are equal. Which parameter is decided? Which non-dimensional is decided? Just comment which non-dimensional. Prandtl number. Which number is decided? Prandtl number. So Prandtl number, it is a number, you think that it connects between fluid mechanics and heat transfer. So anyone ask you कि which non-dimensional throughout in the world that connects the heat transfer and fluid mechanics, you can say that yes sir, Prandtl number. Yes sir, Prandtl number. Okay. ठीक है, thermal diffusivity, and this is your meter square per second, right? And this is your, what is the thermal diffusivity? Thermal conductivity K by rho Cp. K by rho Cp. Okay, beta. Now, what is that significance? K by rho Cp is alpha. We can write L by T by L square. Now, we can also manipulate KL square L1 by L into delta T divided by rho Cp LQ by T into delta T. We can write like that. We can arrange from numerator and denominator. What is that? K L square. We can arrange like that. So finally, if you can arrange this is as this much, this equation. So this is what beta, see the beauty. This is what beta, this is a conduction. Why? Because there is a K, and this is your store. This is your store. See beta, how the rate of conduction takes place with respect to store. Rho into Cp. Rho into Cp, it is a stored phenomena. It is stored with respect to volume. Cp is also stored with respect to mass. And per kg, how much the energy will store, that indicates Cp. And per unit volume, how the energy will store, that indicate rho into Cp. So this is your stored energy per unit volume, and this is your energy conduction per unit length. Okay, across per unit length and per unit volume also. So this is your, the first is your the rate at which heat is conducted across L of the body of a body per unit volume, that means LQ, right? And this is your the rate at which heat is stored in a body per unit volume. Okay, beta. Now, so simply, what is that? This is your, simply beta, what is your, this one, this is your heat conducted, and this is your heat stored. That means how much heat will conducted as compared to how much the heat will stored. That define the Fourier number. So this is your Fourier number. So the Fourier number, when we applied according to Hissler chart, when the conduction resistance and convection resistance are equally important, right? See why the option B is right when we consider the Biot number. This is the Biot number. This define the Biot number. We'll write here, no problem. What is the Biot number, beta? Biot number is equal to convection at the surface divided by conduction in the body, in body. And if we, this is your heat and this is your resistance is ratio, that means R conduction in divided by R convection out, right? R convection out, and practically this is less than 0.1, and this is known as this. That means what, beta? That means what we can say, that R of conduction in is less than R of convection out. R of conduction, internal conduction resistance is small and convective resistance is large. See the beauty. So the Biot number, when applicable, Biot number is applicable when there is a conduction resistance in is lower than the convection resistance, and Fourier number is applicable. See the beauty. Fourier number is applicable when the conduction and convection both are equal approximately. Okay, so this is your D option. Now we'll go through the next problem. This is your problem. Okay, no problem. It is all done. Okay. This is your question. Just give me a answer, beta. This is your question related to the fin. this question related to the fin. Related to the fin. What is that? What is that, beta? Just read and give the reply. Just read, beta, and give the reply. There is no any water, I think. Okay, no problem. See, heat transfer coefficient. Heat transfer coefficient, that means H value. H value. Heat transfer coefficient over the surface of a fin, right, decreases. That means if there is a fin and the convective heat transfer coefficient H value when decreases along the length of the fin, what is its significance? What is its significance? Its effectiveness whether will decrease, its effectiveness or whether will increase, its effectiveness will remain unchanged, its effectiveness first increase then decrease. What's your option? What's your option? When the H value over the fin surface decreases. That means, beta, if there is a fin, see, if there is a fin, see the beauty, if there is a fin, if there is a fin, okay, any type of fin, and if you draw the H value, H will decrease, that means this is your H and this is your length of the fin L. So H value will decrease, So when we moving from the base to the tip, towards the tip of the fin, the convective heat transfer coefficient, this is called local convective heat transfer coefficient X. We always put here subscription X. So the local convective heat transfer coefficient will decrease. If the local convective heat transfer coefficient will decrease, what is the effect on the effectiveness? What is the effect on the effectiveness? This is your question. So my dear, we know that so first we have to know about what is the effectiveness. See, I give you one short for that. I am asking you, what is your effectiveness? What is your effectiveness? Yeah, what is your effectiveness? How to measure your effectiveness? So, see, there are two terms. One is the efficiency, one is the effectiveness. One is the efficiency, one is the effectiveness. Both are the different thing. Effectiveness, your effectiveness is measured. Effectiveness is measured, beta, when you are not present in that situation. When you are not present that situation, and what is the outcome from that situation, and when you are present in that situation, what is your outcome? This will measure by the effectiveness. This will measure by the effectiveness. That means in your adverse condition, that means you are not preparing well. You are not preparing well for the examination, but your performance is very good. Your performance is very good. That is called effectiveness. That means you have highly effective. That means, see, anyone ask you, anyone say that, sir, this person have a highly effectiveness in this area, effective in this area, highly effective in this area. That means highly active. How it is active? Why? Because if it is not there in that village, so no anyone work will develop. So it is effective. So effectiveness, it is a ratio of heat. That means heat transfer by the fin divided by heat transfer with no fin. When there is no any fin, what is the heat transfer? When there is a fin, what is the heat transfer? That means when there is a fin, so what is the heat transfer? You calculate. And if we are assuming that there is no any fin, how the heat transfer will how much the heat transfer will develop? That ratio measure the effectiveness of this fin. That means effectiveness is equal to heat transfer from the fin divided by heat transfer with no fin. So heat transfer by fin may measure on the base of the plate, but that base plate will select the cross section. That means if there is a 0%, see, if there is a base plate, so what is, when there is a no any fin, so this is your fin cross section. So over that, what is the heat transfer? That is no fin. So in this case, we take the cross section of the fin. In that case, we take the cross section of the fin over which there is no fin is present. So same area you take either present or no. Now do not take total base area when you calculate no heat transfer by the fin. Okay, so beta, we take any example. That means in general we take a long fin, right? We take a long fin. So take, you may take any type, any cases, either adiabatic, that means tip is insulated, or a long fin, short fin, anything. So we take long fin. So long fin, beta, if there is effectiveness of long fin is what? Root under HP, Hindustan Petroleum, HP K into cross section area into delta T divided by H into cross section area into delta T. Okay, so you cut it all the things. So this is your heat transfer with a fin, and this is your heat transfer without a fin. So this is your root under Kp by HAC. Root under Kp by HAC. See the beauty, that means the effectiveness is directly proportional, inversely proportional to square root of H. See the beauty. That means this question, the motivation of this question is to that you know the effectiveness concept or not. So when the thermal convection coefficient will reduce along the fin length, the effectiveness will increase continuously. That means if there is a diagram, this is your length of the fin and this is your Hx, so the x value will decrease along the length of the fin, but the effectiveness is continuously. That means in this direction, effectiveness will increase. That means we want that to increase the effectiveness, of the fin. This is very important. When we increase the effectiveness of the fin, the convective heat transfer should be as much as low. Number first, how the convective heat transfer can be as much as low? When there is a flow have a minimum velocity, that means the advection effect of the flow. Is very minimum. That means the velocity of the flow around the fin is very minimum. That means when the velocity of the flow is very minimum, then we can say that the natural convection. That means during the natural convection, if we apply the fin on the base, it must be the effectiveness will increase. Now see the beauty, my dear. When you are riding a bike, over the engine there must be a protrudes, that means there must be a fin. So when you are moving the bike, the protrude, that means the fin over the engine have encounter with the force convection. Why? Because your speed is high. So in that case you calculate the effectiveness. Now the same bike is stopped down on the red light, at the front of red light. So at that point, the engine, which is the produced, that means the fin have encounter with the natural convection. So same fins encounter with the natural convection when it is stopped in front of a red light, and same fin will encounter when the bike is riding. So when the bike is stopped at the red light, the fin effectiveness is high. So you cannot say that ki sir, if we design a fin, will always a fixed effectiveness. No, the effectiveness will depends upon the many factor. That means, see, if we design the fin, the K value is fixed. Why? Because this is the thermal conductivity, that means property of the material. That means if you design the aluminum fin, K value fixed. If you design the fin, parameter is fixed. If you design the fin, cross section area is fixed. So if we change the effectiveness, only possibility is that to change the H value. How it will change the H value? I am already giving you one example. That means you should have to apply the fin. Yeah, you have to apply the fin where there is a possibility of natural convection. Yes or not? Yes or not? Okay. So in this question, its effectiveness will increase. Option number B, its effectiveness will increase. Now, next problem, beta. Next problem. Yeah. This is the next problem. This is your basic concept. This is your basic concept related to the thermal circuit. Yesterday we will solve that one thermal circuit which is a composite wall. That means there is a foam, then there is a plaster, then there is a bricks, right? So at that situation we can analyze the thermal circuit. Now in that case again, so first read the question carefully. A steam at, there is a free steam temperature T1 is 320 degrees centigrade, flow in a cast iron pipe with thermal conductivity 80 watt per meter degree centigrade, where the inner and outer diameter are D1 and D2, where the inner and outer diameter is 5 centimeter and 5.5 centimeter. That means there is a tube have a thickness this much, 0.5 centimeter of thickness, right? Respectively, the pipe is covered with 3 centimeter thick glass wool. See, the glass wool is a very good and very easily available for the insulating material. So cover with a 3 centimeter glass wool insulation, and see the beauty, the thermal conductivity of the insulation is very low. Why? Because there is a very minimum conduction through the insulating material. So this is your 0.5 watt per meter degree centigrade. Heat is lost to the surrounding at T infinite 2 is 5 degrees centigrade. Heat is lost to the surrounding by the natural convection and radiation. This is very important. The heat will transfer which mode? Convection and radiation, but particularly the convection is a natural convection. That means there is a no velocity effect is there. Okay, no problem at all. With a combined heat transfer coefficient is H. That means a combined heat transfer coefficient H value it is given, right? Taking the heat transfer coefficient of inner pipe is this one. Watt per meter square degree centigrade, per meter square degree centigrade. Okay, it is right there. So this is your H2 value, this is your H1 H2 value. That means outside with a combined heat transfer coefficient itna. That means outside H2. This is your transfer coefficient inside. That means H1. So H1, H2, all this. The temperature drop across the pipe shell is ... This is beta NAT type question. NAT. Be careful for this question. Okay, beta. So what is the temperature drop across the pipe shell? So first draw a pipe shell, no problem at all. So this is your pipe shell. See the beauty, beta. This is your pipe. Okay, see the beauty. This is the circle, very good circle on the hand, drawing on the by the hand. See, this is the circle. Yes, I know I am good presentation. I have a good presentation. This is your a tube. This is your tube, beta. Right? This is your tube. And this is your insulation. That means this is your tube over which there is a insulation. So this is your insulation. This is your insulation. This is your insulation. Okay. And this is your tube in which there is a steam. In which there is a steam. This is your tube center. And heat loss from this one. Heat loss from this one. Now beta, this is your steam. This is your R1. This is your R2. This is your R3. Yes or not? R3, R2, R1. Okay, R2, R3, R1. Right. Okay, now we draw the thermal circuit. This is the steam at inlet. This is the steam at inner. You can also be draw like that, beta. If there is a pipe and over there is a insulation is there. Okay, so this is your T infinite inner side. This is your T infinite outer side. So draw the thermal circuit. This is your convection at the surface. This is the conduction within the pipe. This is again conduction in the insulation, and there is a convection outside T infinite too. So there must be 1, 2, 3, 4 resistance. There must be 4 resistance. Now this is your Ri. This is your Ri. This is your R1. This is your R2. This is your RO. This is your T1. This is your T2. This is your T3. So T1 is the inner side temperature of the wall. T2 is the outer side temperature of the wall. T3 is the outside of the insulation. T infinite 2 is the outer temperature. Right. Now, if there is no any information of the pipe length, take length of the pipe is 1 meter. Take length of the pipe is 1 meter. Right. If there is no any information is given, so take length of the pipe is 1 meter. Now, see, there is both side fluid. That means inside and outside. Both side have a fluid. Both side fluid. Mind it. Both side fluid. Both side fluid. So surface area exposed to the convection. So the surface area exposed to the convection is A1 is the inner side is what beta 2 pi R inner R1 into L length. Outer side A2 is 2 pi R3. For the speed calculation, during the speed calculation, you put A2 is equal to, you can have a mistake that A2 is equal to E2 in place. When you put A2 value 2 pi R, so there may be a chance then you put R2 and all the calculation gets fall. Right. So this is your R3, mind it, into L. So this is important. Okay. Right. So put all this value. 2 pi R1 is 0.025 into L is 1. So this is how much beta? 0.157 meter square. Now this is what beta? 2 pi into R2. R2 is 0.057. No. This is 0.0575 5 it is given into 1. This is your beta 0.361 meter square. Now we calculate all the resistance. Ri is convection resistance is equal to what beta 1 by Hi into A1. So 1 by Hi it is given how much? 60. AI we have A1 we have 0.157. So this is your 0.106 degree centigrade per watt. Degree centigrade per unit watt. No problem at all. What is R1? This is R1 is R of pipe. This is R of pipe. What is R of pipe beta? This is a cylinder. So this is your Ln R2 by R1 divided by 2 pi L K1. K is the thermal conductivity of pipe and K2 is the thermal conductivity of the insulating material. Insulating material. So this is K1. Now beta put all this value. Ln R2 is what beta? R2 is, just to calculate, 2.75. Why? Because all the dimension it is given. R1 it is your 0.025 divided by 2 pi L is 1. K1 it is have 80. So this is your 0.0002 degree centigrade per unit watt. So this is your Ri, R2. Now you calculate R2. R2 is what beta? R of insulation. And R of insulation is Ln R3 by R2 divided by 2 pi L K2. Put all this value. Ln R3 is what beta? R3 is 0.0575 divided by R2 is 2.75 divided by 2 pi L is 1 and K2 is very minimum, that means 0.05. Put all this value. This is your beta 2.35 degree centigrade per unit watt. Now we have to calculate RO. So RO is equal to 1 by HO into A2. So 1 by HO it is given. Yes, it is given 18. A2 you already calculate 0.361. So this is your 0.154 degree centigrade per unit watt. Now, what is R total? R total summation of all this R1, R2. Why? Because this is in series beta. This is in series. So R of total is equal to Ri, R1, R2, RO. Yes or not? If you put, this is your 2.61 degree centigrade per unit watt. Now, heat loss from the pipe. What is that? Heat lost from the pipe. Sorry, from the pipe is, what is that? From the pipe is T1 minus T2. Yeah, T2 minus T1 divided by this R1 radius. So first we find the heat transfer. So heat lost from the pipe is not from the steam. This is equal to T infinite inner temperature, T infinite outer temperature divided by R of total. T infinite 1, T infinite you have 320 minus 5 divided by 2.61. This is your 121 watt. So this is your heat transfer from the. So what we can calculate? Temperature drop across the pipe, delta T of the pipe. This is what? Heat transfer into thermal resistance of the pipe. So what is heat transfer? 1 to 1 into R of pipe is what? R of pipe is R1. R of pipe is R1. See? R of pipe is R1. So R1. So in place of R of pipe, we can write R1. Don't confuse. So R1 is what? 0.0002. This is your 0.02 degrees centigrade. This is your temperature difference between the inner side of the pipe, inner wall temperature of the pipe, and this is what, beta? Inner side. That means T inner side minus T outer side. This is temperature. Okay? This is your temperature. It is clear, everyone, please? It is clear, beta? Everyone, it is clear? Now, we take these questions also. See, why we take this question? Why? Because it will recapitulation of your non-dimensional number again. See, I already gives that the dimensional quantity that connects between the velocity flow field. This is very important. Velocity flow field and temperature field. And temperature field. Velocity flow field and temperature field. That means velocity profile and the temperature profile. See, beta, if there is a plate, see the beauty, if there is a plate, right, and this is your y direction and this is your x direction, beta. This is your x direction. So this is your flow. This is your flow. Yes or not? This is your U infinite and T infinite, free stream temperature. Okay, U infinite and T infinite. Now we take T infinite and this is your wall temperature. This is your wall temperature, T wall. We take T wall is greater than T infinite. T wall is greater than T infinite. So there must be a heat diffusion from the wall to the fluid, heat diffusion, and there is a velocity, so there must be a momentum diffusion from the wall to the fluid at that point. So during the momentum diffusion and the heat diffusion, there must be a growth of a boundary layer, which is velocity boundary layer and thermal boundary layer. So it may be, so the growth of a boundary layer is due to the diffusion phenomena. So growth of a thermal boundary layer may be this one, and growth of a hydrodynamic boundary layer may be this one. So this is your hydrodynamic boundary layer. Hydrodynamic boundary layer, and this is your thermal boundary layer. This is your thermal boundary layer. This is your hydrodynamic boundary layer. This is your thermal boundary layer. Now, if we think that at any particular cross section, this is your velocity thermal boundary layer. This is your delta H, delta T, and this is your velocity boundary layer, delta hydrodynamic boundary layer, delta H. So beta, in this case, delta H is higher than delta T. That means momentum diffusion, that means the diffusion of the momentum is higher as compared to the thermal diffusion. So that boundary of the thermal boundary layer is within that the velocity boundary layer. It may be that the thermal boundary layer is more than the hydrodynamic boundary layer. In that case, the diffusion of a heat is more as compared to diffusion of the momentum. So this depends upon the momentum diffusion. So there must be a, this will decide there must be a Prandtl number which is decided by hydrodynamic boundary layer divided by thermal boundary layer पे power q. This is very important relation. Always 1 mark question in the gate will ask this concept, 1 or 2 mark. So this will decide which hydrodynamic thickness, which thermal, which boundary layer, this is your boundary layer, which boundary layer thickness is higher, that means, see beta, see if the Prandtl number is greater than 1, that means hydrodynamic boundary layer is higher than the thermal boundary layer. If the Prandtl number is less than 1, then in that case hydrodynamic boundary layer is thickness is less than thermal boundary layer thickness. That means thermal boundary layer above that the hydrodynamic boundary layer. And if the Prandtl number is approximately 1, then both the thermal boundary layer are overlap. That means there is no any demarcation between the thermal boundary layer and the hydrodynamic boundary layer. So this is the case from where the thermal boundary layer and hydrodynamic boundary layer are overlapping to each other. Right? So the linkage between the temperature profile, this is your temperature profile, and this is your hydrodynamic boundary layer, there is a velocity profile. The linkage, this is your velocity profile and there is a temperature profile. Linkage between the Prandtl number is the Prandtl number. And one very important information, this is first information, basic first information, and second information is that beta, someone asks you Prandtl number, Nusselt number, Reynolds number and Grashopp's number, in which number have the property of a fluid, which decide the property of the fluid. Please anyone please reply. Nusselt number, Prandtl number, Reynolds number and Grashopp's number. In these 4 numbers, which numbers gives the information about the property of the fluid? The answer is same, sir, Prandtl number. Why? Because beta, Prandtl number, in that Prandtl number, all the quantity involved in the Prandtl number, all the quantity will be related to the fluid property. So it is a fluid property. That means if the fluid is fixed, this property is fixed. But all these things, Nusselt number, Reynolds number, Grashopp's number, these are not a fluid property. These are not a fluid property. That means if the fluid will fix, but this number may be changed. So you can see that in the Nusselt number you can write NUX, in the Reynolds number you can write REX, in the Grashopp number you can write REGRX. But Prandtl number you can never write PRX. It is wrong. Always PR. Why? Because it is a fluid property. It is not a local property. But all these are a local property. This is also one important observation. Okay? Now, this is okay, beta. So this is some information related to the Prandtl number. Now next question, see. Yes, this is our very important question also. Very important question. Okay, this is also very important question. Read that question beta carefully. Read the question carefully. First. It is very important. I read the question. 2 meter and see, I will match the question is also whether it is not a typing mistake or not. A 2 meter cross 3 meter flat plate is suspended in a room. That means there is a room and the flat plate is suspended and subjected to air flow parallel to its surface. That means a plate is suspended. Hi Sita, hello. Hello Sita, hello. But you are all again late. Huh? How can you understand the concept? You are late, guys. But don't worry. I always motivate you. And you also motivate me. Okay, beta. So, beta, see, there is a plate. Over the plate, the fluid is flowing and the fluid will contact both side of the plate. So mind it, here the surface area, what you take, the both surface area. You doesn't take the only one surface area. Why? Because the fluid will glide over the surface for both of the surface, not a single surface. Okay, beta. So the plate have a dimension is given. The plate dimension is given. Okay, subjected to air flow parallel to the surface along. That means the flow of air is along 3 meter side. This will give the information about the which dimension we take the characteristic length. So the for the external flow will take always the characteristic dimension is along the flow direction. Always we take the characteristic length along the flow direction. That means if the flow is in the direction of 3 meter, so characteristic length is the 3 meter. If the flow is in the direction of 2 meter, so characteristic length is 2 meter. But this is only for external flow. It is not applicable for the internal flow. Keep in mind. Next, the free stream temperature and the velocity are, it is given. What is the free stream temperature? What is the free stream temperature? It is given. That means this is T infinite. And the velocity of it is given free stream, that means it is a u infinite. That means a free stream properties are given. That means a temperature of the fluid and velocity of the fluid. Right. The total drag force. This is the question which is highly recommendable and within the linkage of the fluid mechanics and the heat transfer. This is very beautiful example which relates the fluid mechanics and heat transfer. Okay, the total drag force acting on the plate is measured to be this one. That means what is the drag over the plate? This is also given. This is also given. Okay, drag force. That means if there is a plate, if the air will glide over the air is want to drag the plate in the direction of the motion of the plate. Okay. Right. The average convective heat transfer coefficient for the plate is. So average convective heat transfer, you want the convective heat transfer coefficient. This is very important question. That means beta drag coefficient. One is the drag coefficient, one is the convective heat transfer coefficient. So in the fluid mechanics we find the drag coefficient, in the heat transfer we find the convective heat transfer coefficient. See the beauty. If you have a drag information, how to find convective information? This is the beauty of this question. This is the beauty of this question. That means if you have a drag information, why? Because if you have a fluid mechanics information, how to find the heat transfer mechanism, heat transfer information. That means this is the question to build your, if the property of the fluid mechanics is given, how to find the property of heat transfer. Okay, beta. So how to find the convective heat transfer coefficient? This is a very important question. Okay, so some properties are also given. What is that, beta? So there is one density of air. The density of air, it is given 1.204 kg per meter cube. This is the density, right? Okay, no problem. And this is your Cp. Specific heat capacity is 1.007 kilojoule per kg Kelvin. And there is a Prandtl number, it is given. See the beauty, the Prandtl number is absolute form. It is not a local. Why? Because it is a property, right? So it is also given 0.7309. That means there is air in the subjected to airflow. So this is the Prandtl number of the air. Okay. Now, how to find? Please see. This is my favorite question. That means if there is a plate, beta, if there is a plate suspended in a room, that means there is a room, or in the room the plate is suspended. See, where we can find this type of situation? Quenching. If you have a quenching process in the industry, if there is a plates, a big plates have a very large plate, and you want the quenching that, so you just you just hang the plate over the ceiling and you flow the air from the base so that the quenching process is for. That is called air quenching. So this example will done in the production department, where you have to quench the material from the air passed over it. So there is a plate hanging over the ceiling and air is flowing over it. That means this is your flow of air, flow of air, flow of air, either top or bottom, no problem, either top or bottom, no problem, flow of air. This is your air, and the air, it is given 20 degrees centigrade and 7 meter per second. This is given, beta. This is given. Okay, no problem at all. Right. The length of the plate, it is also given. How much? The length of the plate is 3 meter. 3 meter. That means the plate length, it is also given 3 meter. And this 3 meter is along the flow. Already in the question the information is given. Okay, no problem at all. This is given. Now here we can take characteristic length. LC is equal to 3 meter. Why? Because it is an external flow along the dimension. We take flow along the dimension and flow along the three side. Both side of the plate are exposed to the air. Both side of the plate exposed to the air. Both side. So what is the total area of the surface? Total area of the surface is, don't forget, W into L, but there must be a 2. Many students get mistake here. Okay, well done, mistake here. So what is that, beta? What is the surface? 2 into width, 2 into height, length 3. This is how much? This is your 12 meter cube. This is the total surface area over which the air will encounter to the plate. Now, my dear, the drag force, it is given. The drag force, it is given. What is the formula of the drag force? What is the formula? See, the drag force is nothing. It is a dynamic pressures, like that. So the drag force is FD is equal to, you know that, CD, drag coefficient, CD into surface area AS into half rho V square. How to remember it, beta? How to remember? See, we know that beta, stress is equal to, see, drag coefficient CD, it is the ratio of shear stress divided by pressure force, half rho V square. This is your pressure energy, and this is your pressure. This is your pressure and this is your shear. Okay, beta? So this is your dynamic. Okay, so if you find the force, stress force by area is what? Surface area. Now you can rearrange this. So this is your drag force. This is your drag force. This is your drag force. Now put all this value. So from here we can find drag coefficient is what, beta? Is what? 2FD divided by rho AS into V square. So 2 drag force, it is 0.86 divided by density, you have 1.204 into 12 into 7 square, velocity it is given. So how much is this one, beta? 0.00243. This is your drag coefficient CD. This is your drag coefficient CD. Now, if you have a drag coefficient, you must be a relation. What is that, beta? You have, remember this relation. This is very important. Up to this, there is a fluid mechanics. Now, there is a heat transfer. The concept is opening here, heat transfer. What is that? According to, this is your one. Clinton-Colburn equation. Clinton-Colburn analogy. Colburn analogy, you may say that Colburn analogy. What is that, beta? Drag coefficient by 2. This is your half H rho Cp into V into Prandtl पे power 2/3. This is very important relation, beta. This equation, if someone asks you what is the strong equation that will connect between the fluid mechanics and heat transfer, so this is the best example of this equation. That means this is the fluid, this is your fluid mechanics and this is heat transfer. So CD by 2 is equal to H by rho Cp. Always remember, beta. You always remember. Now you have CD, you have rho, you have Cp, you have velocity, you have Prandtl number. From this equation, you can easily find what is your H value. So CD you have how much CD? How much CD, beta? CD your 0.00243 divided by 2. This is equal to H. H you have to find it divided by, put all this value, rho 1.204 into Cp you have 1.007 into V you have 7. This is equal to into Prandtl number you have 0.7309 पे power 2/3. My dear, I am requesting you that please, the here is be conscious for the calculation. 99% student gets calculation mistake here. So when you are putting all the given data, then you have to chance to calculate that equations to solve that a particular value. Just be patient, otherwise you make definitely get a mistake here. So be careful. So what is the H value? The convective heat transfer. The convective heat transfer is, if you calculate, just it is your 12.7 watt per meter square degree centigrade. This is your answer. This is your right answer. Okay, beta. So this question is also very useful. Why this question is important? Why this question is important, beta? This question is the logic is that the answer is that that it involves the fluid mechanics concept. So in the GATE, beta, such type of questions is a highly probability that they are connect 2-3 subject in a one questions. That means in this question we connect fluid mechanics and heat transfer, so that this questions is very important. Number first. Number second, this is also, there is a application of one formula. That means you know the formula of this one or not. Second. Number third, if you do the very fast manner calculation, you get a mistake. So there may be a mistake in these questions. So this questions is important for the three perspective point of view. This question involve multiple subject. This question involve a great formula. This is the greatest formula in the heat transfer chapter with subject beta. In the heat transfer subject, this is a very important formula. Number second. Number third is the calculation. So this question is very important according to me. Right. Now, next. This is your next problem. This is your next problem, beta. Just solve it, beta. This is your next problem. So this is your heat exchanger problem. This is your heat exchanger. This is your heat exchanger problem. What is that? I will first read and we'll also match the question. A home air conditioning system use a counterflow heat exchanger to cool 0.8 kg per second of air. That means we want that a cool the air from 0.8 kg per second from 45 degrees to 15 degrees centigrade. That means if we want that the air has to be cooled from 45 degrees centigrade to 15 degrees centigrade, right? No problem at all. The cooling is accomplished by the steam of the cooling water. That means the cooling will done by the steam of the cooling water that enters the system. With the mass flow rate, it is given 0.5 kg per second. Now, the flow rate at, this is okay or not? The flow rate at 8 degrees centigrade temperature. This is the flow rate. System with a 0.5 kg per second flow rate at 8 degrees centigrade temperature. Right, beta? If the overall heat transfer coefficient, this is your U value. Overall heat transfer coefficient U. Overall heat transfer coefficient U, it is given. The number of a transfer unit and heat exchanger area required. That means in this question, what you have in NTU, number of transfer unit, and what is the area which is required for the heat transfer. What is the area which is required for the heat transfer? So this is your option C. This will take a property, that means Cp of the air 1.005 kilojoule per kg Kelvin and Cp of the water is 4.186. Okay, now we solve this problem. This is the problem related to the effectiveness and NTU method. Effectiveness and NTU method, which chapter this concept is involved? This concept involved in the chapter of heat exchanger. The chapter of heat exchanger. Now, we'll solve this problem. No problem, beta. What is that? See. So first, this is also given sometime, beta. It is given in the question also. This is the counterflow na. For the counterflow, generally effectiveness it is given formula in general. Otherwise, you can remember it. Effectiveness is equal to 1 minus EXP minus NTU 1 minus C divided by 1 minus C exponentially minus NTU 1 minus. Okay, beta. So this is your effectiveness. It is given. It is given. It is given. Okay, beta. Now, see, this is your counterflow heat exchanger. So we draw temperature versus length diagram of the heat exchanger. This is your x direction of the flow. This is your temperature direction. Right. This is your counterflow. So there is a length of the tube. This is your x is equal to 0. This is your x is equal to L. Now, in this there is a hot fluid and this is your cold fluid. Okay, so this is your hot fluid and this is your cold fluid, right, beta? So this is your THI, THE, TCI, TCE. Exit temperature, inlet temperature, all this temperature it is given, and this is your air. Air, with the air we cool the water. This is air. From air we are cooling, and from the water, steam, water, there is a water. From the water we can calculate, we can cool the air. That means this is a type of air preheater. this is your mass of water. It is given how much? 0.75 kg per second. And mass of the air, mass flow rate of the air, it is also given how much beta? 0.8 kg per second. This is also given, right? THI, it is given how much? 45 degrees centigrade, right? THE, it is also given 15 degrees centigrade. TCI, it is given 8 degrees centigrade. This is given. Okay. Now, the overall heat transfer coefficient, it is given how much beta? 35 watt per meter square Kelvin. It is also given. Now, how to solve? This is a very easy problem beta. Definitely, it is a very, very easy problem. What is that? See, there is a one step. First, find capacity rate. Capacity rate, C. C capacity rate, C. So, C you have to find for cold fluid. That means m dot C, CPC. C have to find for hot fluid, m dot H, CPH. Now, what is m dot CPC? Just to calculate, the mass flow rate is 0.75 and CPC is 4186. If you solve this one, this is your 3139.5 watt per Kelvin. If you solve this one, this is your 0.8 into CPH is beta 1005. If you solve this one, this is your 804 watt per Kelvin. See the beauty, in which value the C is minimum. The C is minimum, it is in m dot H CPH. So this value is minimum and this value is maximum. Yes or not? This value is minimum and this value is maximum. Now, you find the capacity. This is your capacity rate. Now we have, this is your capacity rate and we have to find, this is your capacity rate. Matlab C, this is your CH and this is your CC and this is your CH. This is your capacity rate, not C. CH and CC. Now you have find capacity ratio. Capacity ratio. What is that? C. This is your C minimum by C maximum. What is the C minimum beta? 804. And what is the C maximum? 3139.5. Now you have solved this one. This is your 0.25 C. So this is your C value. Now, what is the effectiveness? We know that. If we take C minimum is this one, C minimum is this one, CH, put energy at that CH in top denominator and denominator we put the maximum. That means actual heat transfer, Q actual heat transfer divided by Q maximum heat transfer. So, actual heat transfer, maximum heat transfer is what beta? Maximum heat transfer is what? C minimum into maximum. What is the maximum? THI minus TCI. THI minus TCI. And intuitionally put in the numerator at actual, that means this is your C minimum, and C minimum is your hot fluid. Then put here C hot into hot fluid THI minus THE. So this will cancel out, yes or not? So this is your effectiveness. Put all this value, that means 45 minus 15 divided by 45 minus 8, and this becomes 0.81. This becomes 0.81. So this is your 0.81 effectiveness you have. Now you have a formula, see, for the effectiveness. From this formula, we can easily find what is NTU, right? What is NTU? So NT, we know that given efficiency, effectiveness you have 0.81 is equal to, otherwise you can solve it first. Why? Because the calculation is very lengthy for that. So easy to calculate. 1 by 1 exponentially minus NTU 1 minus C divided by 1 minus C into exponential minus NTU 1 minus C. First write down and then little bit arrange it, rearranging. How to rearrange? Just you cross multiply. So effectiveness minus 1 divided by effectiveness C minus 1, this is equal to exponentially minus NTU 1 minus C. Now put all this value. Effectiveness you have 0.81 minus 1, 0.81 into C, C is 0.256 minus 1 is equal to exponentially minus NTU and C, 1 minus C, C value beta 0.256. So from here we can find easily what is NTU. So NTU, you can solve this equation. Now you can solve this equation. So this equation is NTU 1.92. This is NTU 1.92. Now the next we have to find surface area. Now next we have to find beta surface area. How to find the surface area? How to find the surface area? We know that NTU, this formula we know that U into surface area divided by 1.92. So what is that beta? What we know that U into surface area divided by C minimum. So you have overall heat transfer coefficient. So from here we can write surface area is equal to NTU into C minimum divided by overall. So what is NTU beta? 1.92. What is NTU? 1.92. C minimum you have. What is C minimum? 804. What is the overall heat transfer coefficient? 35. Put this value beta 44.1 meter square. That means this area have to require to transfer the heat. This area will require to transfer the heat. This area is required to transfer the heat. Okay. Now next problem. This is your next problem. We'll check this problem is correct or not. Yes. A long section of 8 centimeter diameter horizontal hot water pipe pass through a large room. That means there is a pipe. That means there is a pipe. Through the pipe a hot water is flowing. Why it is flowing? Why? Because room whose temperature is 20 degrees centigrade. When the 20 degree centigrade room, there is a hot water pipe is passing through it. 8 centimeter diameter. Diameter is 8 centimeter and the room temperature, that means T infinite. This is your T infinite temperature. Okay, no problem at all. If the outer surface temperature of the pipe is 70 degrees centigrade, that means this is the outer surface temperature, it is given 70 degrees centigrade. See the beauty. Relay number. What is your relay number? Now, what's your relay number? So you have to find the relay number and some properties it is also given with a take. take, what is that? Take kinematic viscosity is 1.75 cross 10 to the power minus 5 meter square per second, it is given, and Prandtl number also given 0.7241. 0.7241 it is given. Now we have to find the Rayleigh number. Rayleigh number, it is also a non-dimensional number. That means beta, if you solve this one equation, if there is a pipe, if this is your pipe, no problem at all, right, kept in a large room, there is a large room, okay, this is your room, and pipe diameter it is given how much? Diameter it is given 8 centimeter, and the room temperature T infinite it is given beta 20 degrees centigrade, and the surface temperature it is also given 70 degrees centigrade of the pipe. Surface temperature of the pipe it is given. Now, Samir, sir, why don't you teach in Hindi? Why? Because the crowd is maximum crowd is in South Indian here, South Indian people. So for that, but if you want that Hindi, we will talk in between the Hindi part. But sir, but beta, in the case of technical subject, we cannot supposed to say that there is any language barrier. Just keep in mind what is the question it is given and see the solution very carefully so that you don't require any language. Okay. Now we have to find a Rayleigh number. Rayleigh number. What is the Rayleigh number, beta? What is the Rayleigh number? Rayleigh number is, see, RA over the diameter. This is your Prandtl number into Grashoff's number. See the beauty. Prandtl number into Grashoff's number. Grashoff's number is what, beta? G into beta T of surface temperature minus in surrounding temperature divided by kinematic viscosity S square into the characteristic length, it is dq, I think dq into Prandtl number. This Rayleigh number you should always remember. Why? Because I am damn sure in the coming year in the GATE, it may be asked like that. So this is the same situation. There is must be a formula. There may be a calculation mistake and there must be a concept. So it is also the good model of the GATE problem, right? Now, what is B, beta? If you calculate the beta, what is B? B is the coefficient of volume expansion. Coefficient of volume expansion. Coefficient of volume expansion. Coefficient of volume expansion. Right. The coefficient of volume expansion is that this is the volume change. See very carefully. Coefficient of volume expansion is the change in the volumetric strain with respect to temperature at a constant pressure. That means you do a experiment at a constant pressure over which how the volume change with respect to the original volume of any fluid, that indicates the coefficient of volume expansion. That indicates the coefficient of volume expansion. So the coefficient of volume expansion for why? Because the room there is a flow of what, beta? The flow is the horizontal water pipes, right? So this is your, and the coefficient of volume expansion, this is your 1 by TF, temperature of the fluid, temperature of the fluid, and this temperature of the fluid is calculation over the average temperature between the wall temperature plus surrounding temperature divided by 2. Very important. Once you calculate, you put TF, it is in Kelvin, otherwise it's give the mistake here. Okay, now the wall temperature and surrounding temperature you add and divided by 2, and again it will inversely proportional, then you calculate the beta. So there must be a one trick is there. So this is the very chance, this is a very use, this is very damn sure the chance is that to calculation error here. So keep in mind, it is not like that you have a rhythm and you solve it. It must be there is a some special point over which you think twice and thrice. Okay, so what is TF? So there is a TF, and if you calculate TF, this is 70 plus 20 divided by 2. This is your 45 degree plus add 273 degree. This is your beta. This is your beta. Now, once beta you have done, already all the value is done. So the Rayleigh number RA over the diameter is equal to, put all this away, we are very careful. G, acceleration due to gravity 9.8. Beta you have 1 divided by 45 plus 273. This is the coefficient of volume expansion, right? Into surface temperature 70 minus fluid temperature 20, okay, and diameter, what is the diameter? 0.08 cube, right beta? This is your done. Now divided by, what is the kinematic viscosity? 1.75 cross 10 to the power minus 5 divided by 2. And now many people get mistake here. Why? Because they are forget to write Prandtl number in, forget to write Prandtl number here. So there may be a chance to mistake it, stick here. So write here also into Prandtl number. What is the value of Prandtl number? 0.7241. Now you have calculate this value very carefully. There is a high probability to mistake here for the calculation mistake. High probability for the calculation mistake. Okay. So what is that? What is that? This is your answer is 1.8. If you calculate this, this is 1.867 cross 10 to the power 6. This is your Rayleigh number. It is okay. This is your Rayleigh number. Now, so this is this. So why this question is important? The question is important. Why? Because beta, this is a very good question, which model in the group of 1 mark problem, and also they ask in the NIT type question, where you have to knowledge about the Rayleigh number first. For the calculation of Rayleigh number, we must have a knowledge about the Grashoff's number. And you have the knowledge about the Grashoff's number, you must have a knowledge about the coefficient of volume expansion. And you calculate the coefficient of volume expansion, all the parameter you calculate. Now the final is the calculation of all the formula, all the parameter which is put in the formulas. So there may be a mistake to calculation error also. So that's why on that prospective point of view, I choose this problem so that you have a practice on this level, and there must be a chance to calculation mistake here. So according to that, in that parameters, this questions is very useful for the upcoming GATE examination. Okay beta, now next. This is your next problem. This is the problem related to the radiation. This is the problem related to the radiation beta. This is the problem related to the radiation. What is that beta? See, I am saying that there is any typing mistake or not. a very large parallel plates are maintained at a uniform temperature at a temperature T1, let's suppose 800 Kelvin and T2 500 Kelvin, no problem at all. And the emissivity, that means E2 emissivity, sorry, this is your E1. E1 emissivity 0.2 and emissivity E2 is 0.7, no problem at all. Now, respectively, right? Respectively, as shown in figure, where is the figure? I just draw it. The irradiation, this is very important. What is the irradiation? You have to know. For the upper plate, this is very important. Irradiation calculation for the upper plate. So, my dear, upper plate 1, that means upper plate is 1. So, we draw the plates here. This is your upper plate. This is your lower plate. So, the upper plate labeled 1, lower plate labeled 2. The upper plate E1, it is given 0.2 and the temperature of the upper plate, it is given 800 Kelvin. Lower plate, it is given, what is the temperature? T2, or emissivity is 0.7, E2 is 0.7 and T2 is what beta? 500 Kelvin. Yes or not? So, this is your now the situation over which we can find the irradiation. So, beta, first we have assumptions. What is that? What is the assumptions? The assumption is that both surface are opaque. Why? Because there is some emissivity is given and diffuse and gray. Opaque, diffuse and gray. Both surface are opaque, diffuse and gray. Now, the irradiation, for the upper plate irradiation for the upper plate 1. And upper plate, what is the irradiation? Upper plate of 1, that means G1. Radiation is denoted by irradiation is denoted by G. That means you have to find, you have to find the irradiation of upper plate. Irradiation of the upper plate, right? So G1. Now, if you find the irradiation of the upper plate, so irradiation of the upper plate, we see on what plate we have to calculate the irradiation, that will decide by the other plate. That means the irradiation of the upper plate will decided by the information of the lower plate, that means other plate. That means if you calculate the irradiation of plate number 1, take all the data with respect to plate number 2. So, what is the irradiation? Just a heat transfer, just like a heat transfer, radiation heat transfer. But take a property of a plate 2. Always keep in mind, if you find the irradiation of any plate between the two plate, and with respect to the upper plate, with respect to plate number 1, take all the data with respect to plate number 2. That's it. Okay. So what is that? Ipsila E2 T2 ke power 4. That's it. Ipsila E2 T2 ke power 4. Now you have this is a Boltzmann constant. 5.67 cross 10 to the power minus 8. How to remember? 5, 6, 7, 8. How to remember? 5, 6, 7, 8. How to remember? 5, 6, 7, 8. Like that you can remember it. Okay. Now, what is the emissivity? Eta 2. Eta 2 is 0.7. No problem at all. Okay. And T2, this temperature always kept in Kelvin beta. Radiation in the calculation, in the radiation chapter calculation. For the calculation in the radiation chapter, temperature always kept in Kelvin. Yes. Thank you, Atul. Right? So 5, 6, 7, 8. You can remember it into ipsla 2. Ipsla 2.7. T2 temperature is always in Kelvin. So what is the temperature in Kelvin? This is a T2. That means 500. This is a 500. This is a 500 per power 4. Now you can just calculation of this is the matter of calculation 2.5 kilowatt per meter. See, my dear, why I am choosing these questions? This is very important. Why? Because this is question to find the irradiation, and mind it, many people, many students get confused how to find irradiation. My dear, irradiation is nothing. It is a heat transfer by the other plate. That's it. That means how the irradiation will transfer. That means G1 for the plate 1. So we all take the information of plate 2. So don't confuse how to find the irradiation. Irradiation, it is nothing. It is a look like a heat transfer, radiation heat transfer. In my detailed class, all the information and all the derivation will done already, will done in the class. Okay, so who's a student that attend previously in my class, my class, they are able to understand such type of level of concept. Okay, beta. Now, this is your irradiation. Now, beta, next. This is your next problem. This is again, there is a question of fin. This is questions related to the fin. Read carefully. See, what is this question, beta? What is this question? Read carefully. Very simple, very simple. Okay, beta. So this is question for fin. Okay, read this question. A cylindrical rod. This is your cylindrical rod. Why? The cross section it is given circular cross section. So there must be a cylinder of diameter, rod of 2 centimeter diameter. That means it's a diameter. See, this diameter is 2 centimeter and 25 centimeter long. The fins are 25 centimeter long, right? Projects from a well insulated steam vessel. That means there is a steam vessels. On that steam vessel, that means this is your surface of a steam vessel. On that surface, these fins are attached. Steam vessel at 100 degrees centigrade. From well insulated steam vessel at 100 degrees centigrade into the water, into the air is 30 degrees. This is the language. See very carefully. This is you may be trapped in language also. Okay, so well insulated steam vessel at, that means along projects from, this will project, that means this is your what? Base temperature. That means this temperature you have 100 degrees centigrade. This base temperature you have. Now into air, that means this will projected on the steam boilers into the surrounding medium is air, and that air, that means T in finite temperature, it is given 30 degrees centigrade. free stream temperature, it is given 30 degrees centigrade. Now, the free end of the rod is insulated. That means this end, there is a no heat transfer. There is no chance of heat transfer due to convection. And Q convection is equal to 0 from the tip. That means the tip insulated. That means this is called adiabatic tip. Adiabatic tip. That means heat transfer from the tip of the fin is 0. Heat transfer from the adiabatic tip is 0. Now, the temperature at the free end, if the rod is made of a copper with a thermal conductivity, this is the thermal conductivity of the copper material. So, what is the temperature at the free end? We have to find this phase temperature. What is the temperature of this phase? What is the temperature at this phase? So, we have to find the temperature at the free end if the rod of material have a thermal conductivity 330. Take convective heat transfer coefficient. Convective heat transfer coefficient, that means H is given how much? 7 watt per meter square Kelvin. This is the very easy problem, beta. This is the very easy problem, right? Now, how to solve? See, what is given? First, write given, beta, so that we can easily solve. D, diameter of the fin 2 centimeter. This is equal to 2 into 10 to the power minus 2 meter. No problem at all. Length of the fin 25 centimeter. That means 25 cross 10 to the power minus 2 meter. Right. Base temperature is 100 degrees centigrade. Right. Surrounding temperature, no, surrounding not. This is your free stream temperature is 30 degrees centigrade. Now, convective heat transfer, it is given 7 watt per meter square Kelvin. This information it is given. Okay, this information it is given. Now, we have to calculate first perimeter. P is equal to pi d. There is a pi and d. D is 2 cross 10 to the power minus 2. So, what is the perimeter? 0.06283 meter. Now, you have to calculate cross section area. What is the cross section area? Pi by 4. This parameter we will use in the while solving the question. Pi by 4 d square. This is your pi by 4. So, if you put this value, this is 1.1415 cross 10 to the power minus 4 meter square. Right. Now, see very carefully, beta. See this, the tip is insulated. The tip is insulated. That means this tip is insulated. So, at x is equal to L, only there is a conduction through this one. है कि नहीं? Q conduction. And this Q conduction, if there is a convection, so there is a convection. Right? But this is 0. This is 0. So, what is the conduction? Minus K A of C d theta by d x. This is 0. Theta is the excess temperature. Theta is what, beta? Excess temperature. Excess temperature. Theta is excess temperature, and this is 0. Why? Because convection is 0. So, from here we can write d theta by dx at x is equal to L is equal to 0. This we will use in the boundary condition. So, beta, what is the first boundary condition? See, at x is equal to 0, we are at the base. So, theta is equal to theta b, and theta b is equal to what, beta? TB minus T infinite. This is what, beta? 70 degrees centigrade. No problem at all. Now, at x is equal to L, कहाँ पहुंच गए? Where we reach tip. At the tip, d theta by dx is equal to 0. Right, beta? So this is your two boundary condition. Always keep in mind, this is your two boundary condition. Now, what is M value? M is root under Hindustan Petroleum HP by KAC. Right? H you have how much? 7. P you can calculate already. You calculated already 0.06283 divided by K. Thermal conductivity you have. K value you have na? Ha, yes. See, what is the K value? 330. 330. Right? 33 K value is 330. Right? So 330 into cross section area you already calculated. 3.1415 cross 10 to the power minus 4. Right. Put all this value. This is your 2.05968 meter per power minus 1. Now, if the tip is insulated, so how to find the temperature ratio? See, that means theta by theta b, you always remember for the temperature distribution, cos hyperbolic L minus x divided by cos hyperbolic M into L. Right? At the end of the fin. Right. Okay, beta. What is theta you have to calculate? Theta b 70 degree. Right. Where we can find this x is equal to L. At end we have to find. Okay. So cos H L minus L divided by cos H M into L. So this is cos 0. Cos 0 is 1. So this is your 1 divided by cos H into ML at the end. So this have to be theta, that means theta at x is equal to L. We have, if you calculate this value ML hyperbolic, if you calculate, this is your 61.645 degrees centigrade. But this is not asking, this information is not asking the question. Many people get confused here. This is find the temperature at the, that means this will T at a function of at x is equal to L. So this theta at x is equal to L is what beta? This is the excess temperature at the tip. This is the excess temperature at the tip. So this is T at a function, T at x is equal to L. Mine can find T as the function, T at x is equal to L is equal to this one. And it's 61.645 plus. What is the surrounding temperature? What is the surrounding temperature? It is your 30 degree. So add 30 degree plus 30 degree. So how much it is? It is approximately 91. It is approximately 91.645. This is T is the function of x. Okay. This is the T is the function of x is equal to L. So this is your, why we take this question, beta? Why we take this question? Why? Because beta, this question, one second, this question is related to the concept of insulated tip. Many people get confused here, ki, sir, if there is an insulated tip, so there is no any temperature. No, it is not like that. There is a conduction, na? Continuous, there is a conduction. So that conduction and that heat will never transfer to the outside. So the temperature, what is the temperature at this surface? This temperature is continuously rising. Why? Because there is a conduction. Why? Because there is a surrounding temperature here. So the conduction will take place, but that conduction is never crossed into the term of convection. Why? Because the tip is insulation. So we can first find what is meant by the tip is insulated. Okay, beta? Now, the second thing is that how to apply the boundary condition when the tip is insulated. First boundary condition, it is easy. For any case, the first boundary condition, it is fixed. But the second boundary condition depends upon the situation of the fin. Either fin is adiabatic, infinite, finite length. On that, this depends upon the, that condition depends upon the second boundary condition. So second boundary condition is also very important, and that boundary condition we can find out what is the given situation, whether the fin is infinite length or a tip is insulated. For that we can find the second boundary condition. Now, if you find the second boundary condition, two things already done. Now third thing is that how to find what is the temperature profile during the fin at the tip is insulated. For that we have to remember this formula also. For that we can have a knowledge about this formula. Otherwise we cannot solve this question, beta. Now there must be obviously there must be a calculation mistake. So due to this reason I am selecting this question. I selected these questions. Okay, beta. And it is highly chance to in the upcoming GATE examination, to see in your question paper in a upcoming GATE examination. So this is a like that. This is a very important question. Okay, beta. Now next. Yes, this is our next question. This is our next question, beta. See, what is that? Consider a 0.8 meter height. This is your 0.8 meter height and 1.5 meter wide wall. That means this is your wall. This is your wall. So this is your 0.8 meter height. Okay. Oh, so this is your 0.8 meter, 8 meter wide. It is not like that. Why? Because dimension is changed. 0.8 meter height. Height, I think this is your given thickness. And 1.5 meter wide wall, which a thickness of 8 mm. No. 8 mm thickness it is given. 8 mm thickness. 8 mm thickness. This is 0.8 mm perpendicular to the board, and 1.5 meter it is the length. Okay, beta. Thickness. And the thermal conductivity of this material it is given. Right. The temperature of its inner surface during the in the day, which the room maintained at 20 degrees centigrade. That means inner side temperature it maintained 20 degrees centigrade, while the temperature at outer is minus 10 degrees centigrade. See, this question is very important, that let us see the beauty. When there is a car, when you are riding a car, in the car there is a 20 degrees centigrade, and outside from the car there is a 10 degrees centigrade, and in between that there is a kaach, there is a mirror on that car. So this question is very important. How to, if you ride the car, you see that inside the car there is a condensation. So you are facing very difficulty while riding the car when there is a outside temperature is very low. Why? Because there is a condensation takes place, and that condensation, due to that condensation, you can never clearly visualization what is outside. So there may be chance of accident. So how to design this wall, that means kaach, so that the condensation is minimum to minimum. This is very important. Okay, from that perspective point of view, we can take these questions. Okay, beta, and this is the line diagram which is a force convection. That means there is a motion. That means while you are riding the car, the fluid is flowing over that mirror. The fluid is flowing. See, this is your car, na? This is your car. So while riding, fluid is flowing over. So this is your wall, kaach. This is your mirror. While riding, this is a flow of air. So this, from that, this is the inner 20 degrees centigrade. This is outer minus 10 degrees centigrade. So while the designing of the mirror of the car, This concept is very useful to you. Okay, according to that we can take this question. Okay, no problem. So this is your question. Right, now we will start this concept. What we want, beta? We have to find what we have to find. See, consider A itna the temperature of its inner surface. The temperature at its inner surface. The temperature at the inner surface. That means Ti. That means inside the kaach. Inside the kaach. This is your Ti. You have to find it. This Ti temperature. So that beta you can withstand your condensation mechanism. What is the temperature inside that wall? Inside the wall. Okay, beta. So we have to find it. No problem. Just we draw. So just we draw the diagram. This is your wall, kaach, wall, mirror. Now this is your wall. Okay. This is your T1 temperature. This is your T1 temperature. This is your T2 temperature. Okay. And this is inside the wall, and this is outside the wall. Inside the wall the temperature is given. So now how to draw a temperature profile in the convection and conduction mode? So see, the very important, the inside temperature, this is very important. This is your temperature. This is your temperature, and this is your temperature profile. Always mind it. This is your inner T infinite I. This is your outer T infinite O. This is your T1. Right. No. Now heat will transfer from inside to outside. Heat transfer from inside to outside. Now beta, this is your minus 10 degrees centigrade, and this is your 20 degrees centigrade. Okay, this is your 20 degrees centigrade. Now what is the thermal circuit? Draw it. There is a T infinite I, convection resistance T1, conduction resistance T2, there is a convection resistance T infinite. So there is a three resistance. One is conduction between the wall, other is inside convection, outside convection. Okay, beta. Now we have to find Ri. This is your nothing. This is your R of room. This is a convection resistance 1 by Hi into area. What is your 1 by what is Hi? It is given 10. What is the area? Area is 0.8 into 1.5. Okay, this is your area. Put all this value. This is your 0.08333 degrees centigrade per unit watt. What is R1? R1 is R of wall. R of wall. What is R of wall? L by K into A. What is L? Thickness. It is given 8. Right? 0.78 K into 1.8 into 1.5. How much it is? It is your 0.02083. Right. Now what is RO? What is RO, beta? RO is R outside. Outside. It is what? 1 by HO into A. Put all this value HOA. So this is your 0.02083 degrees centigrade per unit watt. Now R of total you have to calculate. Why? Because all the resistance are in series. So this is your 0.1127 degrees centigrade per unit watt. Now you have to find the heat transfer. What is the heat transfer? T infinite inner side, T infinite outer side divided by R of total. So put all this value. 20, here is the chance of mistake, minus minus of 10. Don't forget that this is a minus. R total is 0.1127. This is your 266 watt. Now, this is your 266 watt. And now, we know that this is your resistance, beta. So, we have to find this. So, just multiply this one. This is your Q you have to. So, what is Q? Q is T infinite inner side minus T1 divided by this resistance. This resistance is Ri. So, you have Ti, T infinite I, you have Ri, you have Q. From that one, you can calculate easily what is your Ti. So, from this is T1. That means this is your inner side wall temperature. Inner side wall temperature, and this is your minus 2.2 degrees. See the beauty. See the beauty. So that there is a condensation takes place. This is a negative temperature. That means inside the car, though there is a though there is a 20 degree centigrade inside the car, but due to the outer temperature is so minimum that this same surface, this surface is minus 2 degrees centigrade approximately. That means over the catch, if you touch that mirror, you find very cool. So it's a negative. That means there is a must be a, and this is a hot fluid. Heat will transfer that fluid, and that fluid is a condensed fluid. So inside temperature, this fluid will condense due to this temperature. This is a very low temperature. Then this temperature is try to condense this one. Why? Because it will lose heat. It will lose heat to this car. And why? Because there is air. See beta, this is your surface, and this surface have a minus 2 degrees centigrade, and there is a surrounding have a 20 degrees centigrade. Obviously, heat will transfer from this to this direction, and there is a flow of air. So that air, heat will, this air will try to condense, and there must be a layer of this surface. So this condensation, in generally, we think that there is an outside condensation. No, this is your inside condensation. The condensation in inside. Then you take a cotton and rub inside the car so that you can easily visualize outside. What is the outside? Okay, beta? So there is a condensation. Why? Because there is a minus 2 degrees centigrade. There must be a condensation. There must be. So how to leave this condensation? How to minimize this condensation? How to minimize this condensation? Just open your window. Just open your little bit window. If you open the little bit window, the heat, this outside temperature minus 10, this will gives the this will condensation, and this will drop to in the form of liquid. Yeah, you want to hot AC, air conditioning, heat pump. You open the heat pump so that the medium is heated, and this will heat, and this will condense in the drop. So they will remove it. Okay. So this is the designing part of that mirror of the condensation. Okay, beta. Now next. Yes. This is the next problem. This is the next problem, beta. This is the next problem. This is also heat exchanger. This is your heat exchanger problem. Okay, what is that? A engine oil at 150 degrees centigrade is cooled to 8 degrees centigrade, cooled at 80 degrees centigrade in a parallel flow heat exchanger. Parallel flow, that means both fluid are flowing in a same direction. Heat exchanger by a water entering water at inlet temperature is 25 degrees centigrade and living at 60 degrees centigrade. Okay, no problem at all. See, this is beautiful. MSQ type question. This is your MSQ type question. Okay, beta. So, which one is the following are correct? The exchanger effectiveness is, we'll check whether it is 0.56 or not. The number of transfer unit is 1.221. Lowest temperature to which, this is very important, lowest temperature to which the oil may be cooled by the increasing the length of the heat exchanger if the fluid flow rate and the inlet condition remains unchanged is. That means, what is the lowest temperature we can achieve? What is this lowest temperature will achieve or not if we enlarge the heat exchanger? That means, see, increasing the length of the heat exchanger, what is their lowest temperature 67 will reach or not? We'll check. Okay, no problem. Heat transfer area also will check. This is very important problem. Okay, beta. Now so this is your parallel flow heat exchanger. This is your X. This is T. X is equal to 0. X is equal to L. Now, there is a oil, there is a water, right, beta? Okay, so there is a THI, THO, TCI, TCO, right, beta? So this is your oil, this is your water, this is your water, this is your 150 degrees centigrade, this is your 25 degrees centigrade, this is your 80 degrees centigrade, and this is your 60 degrees centigrade. All the temperature are given. So from the energy balance, we can find the minimum specific heat. From the energy balance, we can find the minimum specific heat. How, beta? We know that heat transfer by the oil, heat release by the oil will heat gain by the water. That means energy balance. That means energy balance. What is the energy balance? Mass of the hot fluid, Cp of hot fluid, THI minus THE is equal to mass of flow rate of cold fluid, Cp of the cold fluid, TCO minus TCI. Put all this value from here, you can get m dot H CpH, m dot C CpC. If you find this ratio, this is your 0.5. See the beauty. So you can easily say that which is the minimum. This is your minimum value, right? Okay, this is 0.5. So this is your minimum. C minimum, and this is your maximum. C maximum, and this is your C. So you have to find indirectly what is the capacity ratio, right? Now the parallel flow. We know that the parallel flow, what is the effectiveness? 1 minus exponentially minus NTU 1 minus C divided by 1 plus C. Okay, put all this value effectiveness. First, then there is no any information about effectiveness. So find the effectiveness. Effectiveness minimum is what, beta? Minimum is hot fluid. So take hot fluid condition. So this is your actual heat transfer. THI minus THE divided by maximum heat transfer. So what is the maximum heat transfer? THI minus TCI. THI minus TCI. Put all this value, the effectiveness is how much? 0.56. Once you find the effectiveness, from here you can find NTU. So what is NTU? NTU is 1.221. This is number of transfer unit. Once you have to find the number of transfer units, see, will check which option is correct. The if exchanger effectiveness 0.56, it is correct. Number of transfer unit, it is correct. Now next, the lowest temperature will check. Very important, I am telling you. This information is very important. Part C is very important. Part C is very important. Part C is very important. See, the exit temperature, of oil should be minimum, corresponding the situation when the heat exchanger, see beta, very important. What is NTU? See how to solve this question, this is very important. What is NTU? U into AS by C minimum. Yes or not? U into AS by C minimum. What is AS? What is U into AS? Not AC. What is AS beta? Pi D into L. This is your L. See, if we increase the length, the surface area will increase. Yes or not? If the surface area will increase, the NTU will increase. So beta, if we find, very important, if we find in a heat exchanger the temperature is, the outlet temperature of the fluid is very minimum, you should design the length of the heat exchanger is maximum. Once you design the heat exchanger length is maximum, it must be surface area maximum. Once you design the surface area maximum, its number of transfer unit is maximum. That means for the minimum temperature, theoretically NTU tends to infinite, maximum. This is your very important information. Okay, now, so NTU is maximum. So if we put in this one, NTU is infinite, this is infinite, so this is your minus infinite. So exponentially e पे power minus infinite, यानी 1 by e पे power infinite. E के power infinite is a maximum, minimum. So it is 0. So this term, it is a 0. So for the minimum temperature, efficiency is equal to 1 divided by 1 plus C. This is very important, I am telling you. Right, okay. So according to this, should be minimum at effectiveness is equal to 1 divided by 1 plus C. 1 divided by 1 plus C. So what is known to me? What is the effectiveness at this point? When the NTU is maximum, corresponding to that NTU, yeah, when we want the temperature is very minimum, so corresponding to that temperature, corresponding to that situation, what is the effectiveness of a heat exchanger? What is the effectiveness of a heat exchanger? So effectiveness of the heat exchanger calculated by this formula. So 1 divided by 1 plus C. C is what beta? 0.5. So now what is the effectiveness? 0.667. See, this effectiveness will increase or not? This effectiveness will increase now. Why? Because initially the effectiveness will less than this one. So if you want the maximum to maximum heat transfer so that the temperature is minimum, its effectiveness should be increased. See, the effectiveness should be, according to that, this effectiveness, now we can design the heat exchanger. So effectiveness is equal to what beta? This is your 150 minus THE divided by 150 minus 25. And this is what beta? 0.667. Now according to this, we can find THE. This was 66.62 degrees centigrade. So the option is Yes, C also correct. C also correct. Now, the option number D, heat transfer area. To calculate, see, to calculate heat transfer area, to calculate heat transfer area, see, what is NTU? NTU is U into AS divided by C minimum. Now to calculate, we have NTU, we have C minimum, but if you calculate this one, there is AU into AS is what? Now, to find AS, we have to find overall heat transfer coefficient. But there is no any data which gives the information about overall heat transfer coefficient. So the data is insufficient for this calculation. See, very important. This will just a trap. This will just a gives the trap to that you can trap that situation in this option and you can lose your time. So it is very difficult to say, it is very important to think that whether this calculation is done according to the given data or not. Why? Because this is a MSQ type question. So from here, the given information, given input, we cannot find the overall heat transfer coefficient. So we cannot find the surface area, heat transfer surface area. So D option is correct. Okay. So my dear, I hope you enjoy this 2 days session of GATE Booster, and also we have solved very important question, and according to these type of questions, your preparation is up to this level. See, if you in the exam, when you prepare the exam, your level should be above that exam. If you prepare a particular examination, your level is above that. Now when you above that and during when that examination is coming day by day nearer, so your preparation level is low, and that's you enter your exam. So always try to maintain the high conceptual question so that your mind will always thoughts to that given situation. Always give the better solution for that. So you have a practice for not a GATE level, your practice is above than GATE level. Practice always above than GATE level. If you practice at a GATE level, your performance not much better. So the ranker, 100 ranker, all should have prepared above the GATE level, so that you have built your very strong foundation of any subject. Okay, so I hope you enjoy this session. Thank you. Bye-bye.